Welcome back to Chapter 1.3, Part 11 of 11, the finale. In Part 10, we built the sampling distribution by simulation and confirmed its center and spread. Now we look at the one thing the formulas cannot give us, the shape, and watch it transform as the sample grows. Then we point ahead to the two great limit theorems that explain everything we have seen, and send Priya off with a better sticky note. Now the part you cannot get from the formulas, the shape and how it changes with n, we plot the sampling distribution for sample sizes of 10, 50, and 500 side by side. Three things jump out, and they are the takeaways of the chapter. First, all three histograms are centered on the same line at mu, $8,000. Growing n does not move the center, because unbiasedness holds at every n. The recipe always aims true. Second, the histograms get dramatically narrower as n grows, and they narrow at the 1 over root. N rate, going from 10 to 500, is a 50-fold jump in data, so the standard error should fall by the square root of 50, about 7-fold, and it does. This visible collapse onto the line is consistency. You are watching X bar converge in probability to mu happen before your eyes. Third, the shape changes too. At n equals 10, drawing from a skewed loss distribution, the histogram of X bar is still noticeably right skewed. It remembers the shape of the underlying claims. By n equals 500, it has become a clean, symmetric bell, no matter that the individual claims are anything but bell-shaped. That is not an accident, and it is not something we have earned yet. Step back and notice what we did and did not do. We defined the sampling distribution and observed, by simulation, two stunning facts. As n grows, it concentrates on the truth and it becomes normal. We have not yet explained either one. That is deliberate. The two explanations are the two great limit theorems of statistics. The law of large numbers explains the concentration. Why the distribution piles up on mu, the rigorous engine behind the word consistency. The central limit theorem explains the bell shape, why the sampling distribution of X bar is approximately normal for large n, even when the data are skewed. Both are the entire subject of Chapter 1.4, where the sigma over root, n standard error, stops being a formula you trust and becomes the thing you build confidence intervals and, later, hypothesis tests out of. Priya now writes a better sticky note. Not 8,410, but 8,410, standard error about $850. The first is a rumor. The second is an estimate that knows how much to trust itself. To summarize Part 11 and the whole chapter, the sampling distribution stays centered on the true mean, confirming unbiasedness, narrows at the 1 over root. N rate, which is consistency in action, and morphs from skewed to a clean bell as the sample grows. We observe both the concentration and the bell, but explain neither. The two explanations are the great limit theorems, the law of large numbers for the concentration, the central limit theorem for the bell, and they are the entire subject of the next chapter, Chapter 1.4. You now own the vocabulary that makes that chapter possible. Estimator versus estimate, bias, variance, mean squared error, and its decomposition, consistency, and the sampling distribution that ties them all together. Priya leaves with a sticky note that knows how much to trust itself, and you leave ready to prove why it can.